This video is going to discuss DICOM Communications, but before we talk about DICOM Communications, I want to talk a little bit about TCP, the Transmission Control Protocol. So TCP/IP is a suite of protocols that we use for network communication. Of course, DICOM relies heavily on TCP/IP. So I think to understand DICOM Communications, we really have to understand the TCP/IP first. So I'm going to talk about that first. So that's going to be almost half of this video. And kind of relate some of this back to DICOM Communications. And then I'll talk more specifically about DICOM Communications and what's happening within that TCP/IP stack. First, to understand TCP/IP, almost every textbook in the world, if you learn about networking, starts with the ISO OSI model. And I always say that the ISO OSI model is not real. No one's ever implemented the ISO OSI model. Really what we use in reality is the TCP model, which came out around 1981. OSI model came out back in the 70s. So it was conceptual, and it certainly set the stage for for what we have today. There was some thought leaders that came up with this OSI model, and it was definitely something that was used by the folks that developed the TCP/IP model. But the TCP/IP model is the reality that we live in. That is the actual protocol and standards that we use in modern networking. The OSI model is there's no software that supports the OSI model, right? So it's a good conceptual model. I've also heard a lot of people that teach networking and networking textbooks will say things like TCP has 5 layers, and they treat the OSI model as if it's the Bible of networking models, and that all other models are based on that model. And they'll say that the TCP/IP model only has 5 layers because layer 5 contains application presentation and session, right? They'll say it's part of the application layer. And that's completely wrong, right? There are things that, when you look at the OSI model, there are things defined in presentation and session that some of those things happen in the application layer, and some of those things happen in the transport layer. So it's not a one-to-one match. Really, the TCP model is just different, right? It's just a different model. So it's important to understand that. So I'll talk about the TCP model going forward. I'm not going to talk about the OSI model anymore. We'll just concentrate on the TCP/IP model. When we talk about DICOM, NHL7 and all the other healthcare standards, we're talking about the application layer. Most of that is happening in that application layer. And then all of the supporting networking is happening in the transport, network, data link, and physical layer. So let's talk about these other layers first. You've probably heard the term packet, right? Everybody talks about the term packet, but what exactly is a packet? And then we have these other terms, segment and frame. And I think a lot of folks use these terms interchangeably. They'll say packet when they really mean a segment or a frame. Packet is in the common vernacular. Most people don't use the term segment or frame. So what exactly are they? Well, let's say at the application layer, I've got some data that I want to send over a network, right? This is a very simplified example, but let's say I have some data. At the end of the day, everything at the application layer can be converted into binary, right? So we can represent all of our data. We can encode all of that in binary. So for now, let's just take this binary data and we'll just call it data, right? Just for simplicity's sake, we've got some data that's been produced at the application layer. That's going to get passed to the transport layer, where it's going to get encapsulated with a segment. And this idea of encapsulation, or the concept rather of encapsulation, is really important in networking. And what that means is that we don't care what the data is. At that transport layer, the data is completely meaningless. It gets encapsulated with a header and a footer that gives us information about how we're going to handle that data at the transport layer. And then likewise, at the network layer, we take that whole set of information, including the segment, header, and footer, and we encapsulate that yet again with the packet information. So that gets encapsulated with a packet header and footer. And we'll talk about what's in that here in just a minute. And then that gets passed down and gets encapsulated once again as a frame. And that's what's happening at the data link layer. So we have our frame header and footer, and all types of information that go along with the data link layer will be found in that encapsulated frame. And then at the physical layer, it's just binary data, right? We're encoding that binary data on some physical medium that could be wireless or wired or whatever it is, right? We're not going to talk too much about that physical layer in this video. So that's the concept of encapsulation. Again, it's really important to understand encapsulation. I'm going to talk here about all 3 of these middle layers. I'm going to talk about, before I talk about DICOM, I'm going to talk about transport, network, and data link. So the network, and what's important to talk about here is the network and data link layers they're unreliable, They don't have the concept of connections. There's no multiplexing, meaning you can't have multiple applications using it at the same time. So there's lots of issues with just network and data link that we fix with the transport layer. So the transport layer really gives us a lot of features that make the TCP/IP model a workable network model, right? Where if we didn't have that, it wouldn't really work. And also, it's kind of interesting to see that we don't have that presentation and session layer in TCP. So the transport layer takes on some of that responsibility, and the application layer takes on some of that responsibility. And I'm going to try to show you how that works a little bit here. But let's start with the physical data link network layer, right? I just want to talk a little bit about the relationship between these and these different standards that we often talk about. At the physical layer, you've got IEEE standards like 100 base TX, 100 base FX, 100 base T, right? All those, 1000 base T, all those different standards we talk about at the physical layer. This defines, the cabling and the, all the interfaces on our switches and routers and so forth. That's all at the physical layer, right? This could be wired, wireless, all those types of standards. That all happens at the physical layer. And at the network layer, if we step up to the network layer, there's really only two protocols, and really the first one, IPX, is kind of going away. There's not many people still using IPX. IP has really become the de facto standard in the industry. We see that pretty much everywhere. IPX is still around. I guess you might find it in a few places, but it's not very common. And then in the middle, in the data link layer, there's a variety of protocols. 802.3 is an IEEE standard. And that IEEE standard can be used with both IPX and IP. And then there's also IBM standard, which is 802.5 token ring, right, or TR. Some of you may be old enough to remember token ring. And that was supported by things like 802.1 bridging, 802.2 LLC, 802.2 snap, right? And then they would support either IPX or IP. By and large, today, almost all of our networks are basically using 802.3 MAC at the data link layer and IP at the network layer. So if we understand IP at the network layer and 802.3 MAC at the data link layer, we should have 95% of our networks covered, right? We can ignore the other stuff. So I'm going to talk about those two, IP and 802.3. So let's start with 802.3b, right? So we're going to talk about the data link layer. At the data link layer, it's a relatively simple standard, right? So let's say I've got a bunch of computers on my network, and we're going to go back in time here and pretend we have a hub, and I'll talk about a switch in just a second, but let's pretend we have a good old-fashioned hub which just broadcasts everything to everyone, right? It receives information, it repeats that same information to everyone that's connected to it. So a MAC address, a lot of you are probably familiar with a MAC address. It contains two parts. There's the vendor identifier, and then you have a node, a portion of the address. And between all 6 of these sections, it should be a unique address, right? This is all defined in the standard. So somebody maintains a list of all the vendor prefixes. So if you look at a MAC address, you can usually identify who the vendor is from that vendor prefix. And they should always guarantee the vendor that the remaining digits or hexadecimal digits are unique amongst any device that they produce with that prefix, right? They can never repeat. If you talk to any old crusty network guys, there's always somebody that's got a couple of NIC cards laying on a shelf somewhere that happen to have the same MAC address, right? Sometimes it happens, but it shouldn't happen. And as long as it's not, 2 NICs in the same network, it's usually okay, and we'll see why in just a few minutes. But basically what happens is, let's say I'm the first computer on the left, and I want to send a message to the computer on the right at the data link layer. And by the way, we don't need the IP layer to send traffic between computers if we're all connected to the same repeater or the same hub. We do to some extent. I'll talk about that later, but because we need the transport layer, which won't work without the network layer. But just from a very low level, traffic can go from one computer to another. But in any event, so if I'm computer A and I want to get information to computer 3, right? You see I made them red on here so you can see the addresses. Computer 3 is all the way on the end on the right. If I want to send traffic to that computer, I basically create a data link header, or I basically light up that circuit with my message, and in my header. So here's my data link header. My origin is A, and my destination is 3. That hub is going to simply broadcast that information to everyone, and 3 is going to say, oh, that's me, I'm 3, the destination is me, so I'm going to listen to this message and I'm going to process this message. Everyone else should just ignore it. Obviously if you have a packet sniffer, you're not going to ignore it, right? That's what a packet sniffer does. It grabs all that traffic regardless of who the MAC address is. And a lot of switches have a port that you can use that will pass through all of the traffic regardless as to which switch port it's going to. And let's just take a look at that here. So if we had a switch, right? So let's switch this hub out and make it a switch instead, which is going to be a little more efficient. The switch is a little smarter than a hub. So when it sees the destination address is A3, the computer on the right, rather than broadcasting it to everyone, it simply connects that. It creates a circuit that goes to that to the fourth machine, the machine on the end. And now we have our communication without everyone else having to distinguish that traffic from traffic they're not interested in. So that's basically how the data link layer works. Now let's step up to IP. IP is a little more complicated, right? So this is defined in RFC 791. So if you read RFC 791, you can read all about how the IP layer works, how the network layer works in the TCP IP model. But basically, so there's our header from the data link layer, and you can see that encapsulates our packet, and within our packet, we have our own header and footer. And in that header and footer, and it's a little more complicated, right? There's some more information here. For example, you have the IP version is in the first 4 bytes, and then the header length is in the next 8, and then the type of service, the length, and so forth. But there's a 32-bit source address and a 32-bit destination address. And that tells us where this is going to go and where it's coming from, right? Just like when you address an envelope. So that's the most important thing that we care about in this presentation is that source and IP address, right? I don't want to teach you all about all of the rest of the stuff here. I've got other videos that can talk about the packet header, but for this purposes, we're interested in the source and the destination IP address and how we work with those. First, just a few words on an IP address. I'm sure a lot of folks know this, but they're basically, like I said, they're 32-bit, right? So it's 4 octets or 4 8-bit numbers. So if you look at an IP address, you can decompose it into its 4 binary equivalents, right, that look like this. So that's 32 bits, which matches up with our packet header, right? It's 32-bit for the source and destination address. And you also have a subnet address, right? So a subnet tells you which portion of that address is the network portion and which portion is the node portion. So in this case, my first, 24, my first 24 bits is the network portion. So there we go, there's 24. So if I were writing down this IP address, I put /24. That means that the first 24 bits of the network address and the last 8 bits are the node address. And if you're in Microsoft Windows, you do 255.255.255, right? Because all ones for each octet would be 255. And it's with CEDAR addressing, right? So CEDAR addressing, which is defined in RFC 4632, you don't necessarily have to demark your network and your node addresses across these 8-bit boundaries. Instead, you can slide that boundary back and forth. So let's say I turned the last two digits or the last 2 binary positions in the 3rd octet as part of the node address. Now I have fewer bits as part of my network address, which allows me to have fewer networks and more nodes per network, right? So I reduce the number of networks, but I have more nodes in each one of those networks. So my 24 is going to change to a 22, and 255.255.255, if I'm in Windows, it's going to be 252 instead of 255 for that 3rd octet in the subnet mask. I went through that pretty quick, but I just wanted to give you a quick overview of what that looks like, and I think I've got another video that gets into much more detail into how subnet addressing works. But let's move forward here and talk a little bit about routing, right? It's important to understand how routing works because that defines how our data is going to make it from one point to another, right? The data link layer doesn't allow routing. At the data link layer, a switch is kind of a dumb device, right? It only understands the MAC address, and the traffic can't traverse across many different switches to get from one network to another. I should caveat that and say that there are many switches today that can do that, but let's ignore that for a second, right? They do some fancy stuff in those switches and software that can bridge different networks at that data link layer. But let's set that aside for a moment. Purely in the standard, the IP layer, the network layer, is where we can do routing between different networks. So let's say, for example, I've got 2 different networks, right? I've got a network on the left that has a switch, a network on the right that has a switch. all these devices have MAC addresses, right, or those 802.3 addresses. Then I've got a router in the middle, right? So my router has an IP address on two different interfaces. So basically my router has two interfaces. Those interfaces face each of my two different networks, and then each of my networks can connect to those interfaces on the router. And notice that the router has two different network addresses, right? One interface is on the 10.11.12 network on the left side, and the right side is the 172.20.21 network. And all the computers connected to that side of the router are in that network. Now look at my packet header, right? And my packet header, which is the second header in there, right? The data link is encapsulating that packet header. My source IP is 10.11.12.13, and so that's going to be the little computer all the way on the left. And then my destination IP is 172.20.21.22, which is the computer all the way to the right. So I want to get traffic from the computer on the left all the way to the right. So at the data link layer, the first step is my computer on the right, it doesn't know how to get traffic to the computer on the right, right? The one on the left doesn't know how to get to the one on the right. So when it sends its packet, all it knows, and this is what our default gateway is, right? So the software in that computer on the left, 10.11.12.13, it says my default gateway is 10.11.12.1, and its MAC address is A3. So even though the destination IP is 172.20.21.22, it sets the destination MAC address to be A3, the one on the router, on that interface for the default gateway. So then that packet's going to flow through that switch, right? The switch knows how to pass it to that router. So that packet's going to flow through that switch. It's going to land on that interface. The router is then going to look at that header, right? It's going to look at that packet header, and it's going to say, okay, I just received this packet. It came from 10.11.12.13. It's got to go to 172.20.21.22. It knows where that computer is. It knows that that's connected to that network on the right side. But the MAC address, the destination MAC address, is set to the router. So the router says, okay, I need to change that destination MAC address. So it's going to change the A3 to an A6. So it's going to match the destination MAC on 172.20.21.22. And then it's going to send that traffic off to that computer on the right side. So what you'll notice here is that the packet header doesn't really change, right? But the data link layer, the frame, does change, right? It mangles that frame as it goes through the router to adjust the MAC address. So everybody knows where it's coming from and where it's going. At the data link layer, because switches are dumb, they only know that data link layer. And then our computer, our router knows the network layer. And of course, this traffic, this could be way more complicated. We could go through many different routers, through many different switches. All along the way, we could be mangling this packet many different times. And you can mangle the packet portion. The IP packet, the source and destination, can also be mangled with things like NATing, right? Network address translation. I'm not going to talk too much about that in this video, but I will talk a little about firewalls just to kind of relate back to that. But understand that could be mangled with some of these different techniques. But as long as you know the basics here, I think we'll be okay. Now let's talk about the TCP model. Again, we're going to look at TCP now. So we talked about the data link network layer, right? The layer 2 and 3. So at the transport layer, right? So we talked about NIC, we talked about IP. ICMP is another standard at the network layer. At the transport layer, there's two primary protocols that we work with. It's TCP, which has lots of applications, and UDP, which has a few applications. UDP I'm not going to talk about in this video. I'm really going to concentrate on TCP because that's what we use for DICOM, HL7. I put XDS on here and crossed it out because that's really web, right? That's HTML, or I'm sorry, HTTP. So I don't have to list that, right? Another protocol already supports that. We'll talk about that at the end of this presentation. But TCP supports all these protocols that we're going to talk about in medical imaging and medical industry in general, most of our protocols. So as far as TCP, just to give you a little bit of background, I talked about how at the application layer and the transport layer, we have to support session and presentation. So in RFC 793, which again was written in 1981 by John Postel, he laid out 6 reasons in that RFC, and you can go read that RFC and read about all 6 of these reasons, and it's really an easy read, this RFC. It's not a super complicated standard, right? But it lays out the 6 things that TCP needs to do for us. We know what network does for us. We know it can deliver traffic from one IP to another. We know what data link layer can do for us with the MAC standard, right? But what does RFC 793 or TCP do for us? Well, first, it gives us basic data transfer. So it can allow a transfer of a continuous stream of octets in each direction with some context between those octets. In other words, we can send data back and forth between different systems. It gives us reliability. So we should have a way to detect that there are damaged, lost, or duplicated packets and that they're out of order. And we know how to handle that. TCP has to give us some mechanism to give us more reliability. IP doesn't have anything that does that. It just says, oh, here's a packet. Let me send it to point B, from point A to point B. And that's it. It doesn't care about reliability. It just does the best that it can. TCP has to layer on top of that and try to add this reliability to that. And we'll see how that works here in a second. There needs to be some flow control. In other words, we can't overwhelm another node, right? We can't send it so much data that it can't process anything anymore and it's dropping information, right? Like when you're trying to learn something and you're sitting in a classroom and the instructor is going too fast and you're not picking up all the information you need, you just start dropping some of it, right? You don't learn it. So the instructor has to slow down, right? You might put your hand up and say, hey, you need to slow down. I'm not getting all this, right? I can't write it down fast enough. So that's flow control. And then multiplexing allows for many different processes to share the same connection, right? Every computer has one IP address. It could have multiple IP addresses, but we don't want to have a different IP address for every application on that computer, on that server or device. So TCP allows us to multiplex. In other words, use the same IP for many different applications. They're using the same IP address. And then connections. We have to maintain a state of a connection. We have to establish a connection between two nodes, and we have to have that context of that connection. So that all of the data that's related, we understand that data is related. So TCP gives us a mechanism to do that. Finally, it defines a little bit about communications with security and precedence, but some of this is still used today, but don't get this confused for network security, which is a much more complicated topic and has a lot more complicated layers. So the segment header supports those 6 goals, right? So we talked about our header for the IP. I showed you a picture of what the header looks like. But now I'm going to show you a header for TCP. But this time I'm going to break down all the different parts of the TCP header. There's a bunch of different parts. So you have a source port and a destination port. So thinking back, at the data link layer, our address was the MAC address. At the packet layer, the network layer, our address was the IP address. Now at the TCP layer, our address is the port, right? The source port and the destination port. So those ports can be anything up to 65,535, right? So from 0 to 65,535 because of the number of bits that are supported in that position. So in my example here, my source port's 2791, which by the way is not valid, but we'll talk about that in a few minutes, why that's not valid. And then my destination port in this case is port 80, right? I'm just showing these in binary because really it's all in binary in the header. Then we have a sequence number. So sequence number is a really big number, right? So it's a range of numbers starting at 0 all the way up to 2 billion, right? 2 billion, 147 million, etc. And then you also have, not only do you have a sequence number, you also have an acknowledgement number. And I'll explain how this works. I don't have a graphic that shows this, but every segment, right? Every TCP segment has a sequence number that tells you which number it is in a sequence. And it has an acknowledgement number. So if you're acknowledging that you received someone else's message, you would put that in the acknowledgement. You take their sequence number and you put it into the acknowledgement. Again, I don't have a graphic in this video. I have another video that shows more detail around that. But so you have your sequence number and your acknowledgement number, and that's how we support the connections, right? That's a couple things actually. So the sequence number and the acknowledgement number allow us to support connections with TCP, and it also allows us to detect failures. So if we know we're missing, if somebody says, hey, I never got your acknowledgement for sequence number 5, we know they never got it, we can resend it. And it also tells us the how to put these messages back together, right? So we know what order these messages go when we pass it back up to the application layer. So a couple goals that we solve there, right? With sequence and acknowledgement, we have connections, we have sessions, and we have the ability, and we add reliability, right? We already talked about multiplexing with the source port and the destination port. Then you have a little data offset that's just a bunch of zeros, right? So you have 4 zeros. You've got another couple zeros reserved for something else that's not really used yet. And then we've got our flags, which tell us what type of segment this is. So when we use TCP, we're not just delivering data back and forth like IP. we have to also indicate, what are we doing, right? Are we creating a connection? Are we closing a connection? Are we using an existing connection, right? So there's some flags that help us do that. You're going to see me use some of these terms in the next slide. And for example, I'm going to talk about a segment that's going to be a SYN, which means I want to open a connection. So we would set the flag for a SYN. Somebody can send back an ACK, so they would set the flag for an ACK. You can have both of them set, so it's a SYN-ACK message, right? And whatever you're not setting for the flag, you just make it a 0, right? So that's how the flags work. And again, I'm going to show you some of these different statuses where we would set those when we set up our connection with a three-way handshake. A window allows us to define how much data we're allowed to send in our segments, right? So how much data can we actually send with each connection before we stop, right? There has to be a point where we say, okay, I sent them a lot of packets. Let me wait and see if they get these before I start sending more stuff, right? This is going to make sure that they're not going to be dropping packets. So that's going to be our window. Then we have a checksum. There's an urgent pointer, some additional options I'm not going to talk about, and then some padding to close out our header. But that's basically it. That's a TCP header. You can go and look up RFC 791 and you can read all about it and you can see what it looks like and get a lot more detail if you want. I kind of kept this relatively simple in this presentation. So let me describe the TCP three-way handshake. Right? So let's say we have a client and we have a server. So first, our client is going to initiate a connection by sending a segment to our server that has the SYN flag set. They're going to have an acknowledgement, or I'm sorry, they're going to have a sequence number and a SYN flag. Then the server is going to send back their own sequence number, and they're going to set the SYN-ACK flag, saying, I got your sequence number. Here's my acknowledgement, and then they're going to acknowledge that. So that's our three-way handshake, right? First, they send a SYN packet with their sequence number. Then the server sends back a SYN and an ACK at the same time with their sequence number and acknowledging the sequence number that was sent by the initiator. And then the initiator sends the acknowledgement back saying, I got your sequence number. Now we have established a connection. So now we have this established connection. We both know what our sequence numbers are, and we can start sending messages back and forth. And we'll, from those sequence numbers, we can tell if we're missing messages. We can put them back in the right order. I know if I need to resend something, right? So then our data starts to flow back and forth. At some point, we're done communicating. So the initiator of the connection is going to tear down the connection. They're going to say, okay, I'm finished with you. They're going to send an ACK fin. So that's a segment that has the ACK and the fin flag set. Then that's going to get acknowledged by the server. And then the server is going to send its own ACK fin to say, I recognize you don't want to talk anymore. So it's going to break the connection from its side. And then the client's going to send an acknowledgement. And at this point, our connection is closed. So that's the process for TCP sessions, right? And this is all supported by our sequence numbers and our acknowledgement numbers that I showed you in that packet header. If you ever run the netstack command on a server, right, it'll show you the various states of a connection. So if you're on a server, you'll see it in the listen state. If you're on a client, some of the states that you might see is SYN sent, established, fin wait 1, fin wait 2, time wait, and then closed. I would say probably the most common that you'll see is on the server, you'll see listen, and on the client, you'll see established and time wait. The other ones you typically won't see. Established and time wait. The other ones like fin wait 1, fin wait 2, you won't typically see those. You won't see SYN sent. That all happens so fast. It's very ephemeral. So you're not going to see those statuses very often. You might catch one, when you run the netstack command, but generally we're not looking for those when we're troubleshooting or when we're running that netstack command. But it's good to understand what the process here is in the connection. So as an example, when we start talking about DICOM, when you go look at RFC 6335, it defines what our well-known ports are. They're from 0 to 1023. And then you have your registered ports, which are from 1024 to 49,151. And then dynamic ports, which are 49,152 to 65,535. RFC 6335 also authorizes IANA, which is a different organization that maintains the port assignments. And if you go look up the port assignments with IANA, right, so you can go to IANA's website, and if you look up DICOM, the official port for DICOM is 11112, so that's a registered port. DICOM TLS is 2762, HL7 is 2575, IEEE 11073 2701 is port 6464, and that's used for medical devices outside of the medical imaging world, right? So that's just, command and control for DICOM devices. SMB uses 5445 according to the standard, according to the IEEE registry. So, you might look at this and say, no, Brian, DICOM is port 104, right? Everybody uses 104. And yeah, a lot of legacy applications do use 104. There's nothing that says you have to use these ports. These are just the accepted, registered, or well-known port numbers. So it's generally best practice to use these, but you don't necessarily have to. Most applications will know that port 11112 is DICOM, but if you use 104, it's going to think it's something else. But does it work? Of course it still works, but it's just not best practice. Now, looking at this diagram, if I am a device trying to initiate a connection, when you bind to a socket to initiate a connection, so if you're an application, you open up a socket in whatever library you're using for TCP/IP, you open up a socket, it's going to that socket's going to get dynamically assigned a listening port number on your side. And that has to be greater than 49151, right? So it's going to start at 49152 and go all the way to 65536, or 535 rather. So again, those are dynamically assigned. They could be anything, right? It's when you create that connection, you dynamically get a port, and that's where those syntax are going to go to. That's where the acknowledgments are going to go to, right? And all the information flowing back to the initiator of the connection is going to come back to that to those dynamically assigned ports. So in this connection, right? These are all the port numbers, right? Everything's going to 11112 on the server side, and everything's going to 64123, which I just randomly picked on the client side. So everything going from the client to the server is always going to 11112, and everything going from the server back to the client is 64123. It's important to note that the payload, right, if I'm sending a file from my client to my server, that file, the payload of that file is only going to 11112, right? That's the bulk of my traffic. It's usually only acknowledgments and control messages that are flowing back to the initiator of the connection. We're going to talk about firewalls here in a few minutes, and I'll talk about how that affects all this. But everything that we do in DICOM, HL7, SMB, all of that stuff is going to happen inside that established area, right? So, all the stuff that I talked about above and below the established state is happening in TCP. But once that connection is established, then we move into DICOM, or HL7, or whatever standard we're talking about. And then when we're done with DICOM or done with HL7, then we proceed with the teardown. That's going to happen at the TCP/IP level. So let's just talk about firewalls just very briefly. I'm going to try to go through some of these slides here, but we talked about transport network and data link. So at the data link layer, we have MAC addresses and protocols. Then at the network layer, we've got the source IP, destination IP, and the protocol version like IPv4 or v6. And then at the transport layer, we have a source port, destination port, our flags, our connection state, right? So we have all this information. All of this information can be used by firewalls for network security, right? So it has access to all of these different headers. It's got the access to the segment, to the packet, and to the frame. And it can use that information. For example, we could allow TCP on port 80 to a certain IP address, or we can block port 25 going out to the internet, right? And we can build all these rule sets and parse them in some order and make some decisions about what we do with traffic. In general, our firewall rules can evaluate any combination of that information that's in all of those different headers. All of that information is available to everything in the segment header, in the packet header, or the frame header, which is TCP, IP, and 802.3 MAC. You can look at the target and source addresses, the connection state, right? So TCP has that connection state. If it's an established connection, I'm going to allow that traffic back through my firewall, for example. We can actually look at the payload if we want to, right? So some firewalls actually look at the content or the data itself. Takes a lot of processing power to do that, right? But theoretically that can be done. There are two basic types of firewalls. Most firewalls are both, right? But there's two basic types of rules. There's stateless and stateful. Stateless is a rule that's applied to each packet, so it's at the packet level, right? So stateless is a packet level rule, which means it's looking at things in the IP level. It doesn't care about the sequence, it doesn't care about acknowledgments, it doesn't care about any of that stuff. It could be at the MAC level, right? Stateless could be at the MAC level, it could be at the IP level. but generally they're not at the TCP level, although they could be. Stateful are rules that happen at the TCP level, and this is because we care about the state of the connection, right? We determine what return traffic is associated with an existing connection. So somebody opens a connection from outside our firewall, and sends it, or a person opens a connection through a firewall. The firewall can be smart enough to know that when there's a return information coming back, when there's a return segment coming back, it knows that it belongs to a connection, so it allows it back through and sends it to the right node. If you're using natting, that is. We haven't talked about natting, but it could do that as well. It considers the sequence of the packets. It knows just like our nodes have to keep track of our sequence and acknowledgement numbers when a connection is stood up at the three-way handshake, the firewalls that are in between all of that are also keeping track of that connection state. They're sort of eavesdropping and saying, oh, this is an established connection. I can pass these messages in both directions. So what it does is the firewall says on that initial connection, here's what I'm going to allow. But once somebody establishes a connection, they're now trusted, and they bypass a lot of these stateless rules, right? Because it's a stateful connection. They can require additional resources to keep track of all that. If you have a router at home, a lot of the home grade routers, a lot of times you have to reboot them. Why is that? Well, a lot of times it's because all of the circuitry that's keeping track of these sequences and acknowledgments in TCP runs out of memory, and it starts dropping that information and it stops working, right? So we reboot it, memory gets cleared, we start from scratch, and everything works fine for a couple of weeks. Obviously, enterprise grade equipment, or business grade stuff doesn't do that, but, it should work for a long time without having to restart it. But that's one of the reasons I think that we see some reliability issues sometimes on consumer grade equipment. So it has to keep track of that state information, whether it's new, established, related, an invalid connection, right? Hopefully a good firewall can detect when someone's trying to hijack a connection. It understands what's happening. There are two basic types of firewalls. I divide them into two types. There's either the Unix, Linux, BSD type, and Cisco. Pretty much every firewall you buy on the market is, if it's not Cisco, it's based on Unix, Linux, or BSD. And then you have Cisco, right? And really, Cisco probably uses BSD under the hood, but it's a trade secret, right? So we don't know. But Unix or Linux-based firewalls are going to use things like IP chains, or IPTABLES or chains. And then Cisco is going to use access control lists, or ACLs. This is not a Cisco course. I'm not teaching Cisco firewall rules, but I want to give you just a basic idea of how they work. You have access list numbers, and then you have a rule that can permit or deny. You tell it whether it's IP or ICMP. You can also tell whether it's TCP or UDP. You give a source IP, the source mask, the target IP, the target mask. And the mask basically says, what range within the source and what range within the target do I want to allow or deny. And then kind of like shell scripting, you have EQ for equals, GT for greater than, LT for less than, and then not equal, and so forth. And then the port number, if you want to specify, a specific port number. So if I were writing an access control list, I might start with access list number 101. I'm going to permit all TCP traffic coming from any IP address, right? That mask basically means anything, right? Because it's 0.0.0 and then any number, that could be in any of those octets. Going to 68.68.68, but specifically that one, right? So my mask is all zeros, meaning it has to be specifically those octets. There's no wild card there. So anything, permit all traffic on TCP coming from anywhere, going to 68.68.68, where the port number is equal to 80, and that's it. So it'll allow all traffic on port 80 to that node, and then I can have another list that says deny all traffic. All other traffic going to that node. So first allow port 80, then deny everything else, right? So I'm saying only allow port 80, everything else gets denied, and that's it. So that could be a rule. And then I could create another access list if I wanted to, access list number 120. And when I'm done creating my access lists, I apply them to an interface on my router. So maybe interface 0 is facing my untrusted internet, right? That's ETH0. And then interface 1 might be my trusted network, right? And I build all the rules for my trusted network, and so forth and so on. So that's what Cisco ACLs look like. IPTables looks a little more complicated only because it's a lot easier to understand what's happening because it's all open source, right? We know how it works. you have a network interface card. There's a post-routing and a pre-routing processor on it. So all of the traffic that comes into the NIC is going to go, or that comes into the machine is going to go to the to IP chains. It goes to, if the traffic coming in on a NIC is not destined for the machine, right, for the machine itself, for that particular machine, it's going to just route it right out to the forwarding rules, and then the forwarding rules are going to send it back out, depending on whether it's allowed to forward it back out. So this is when a Linux machine or a Unix machine is acting as a firewall or as a router, right? It's allowed to move that traffic through. Now, if traffic comes in and it's destined for that machine, it goes to the input chain, which decides whether or not to allow that traffic to go to a process within that Unix or Linux machine. And if a process generates network traffic, it goes to a routing chain, which then goes to output, where again it goes through a series of rules and then it gets routed out, right? So we have the IP forwarding rules. So there's the forward chains, the input chain, and the output chain. Those are usually the ones we're concerned with. So IP or the forwarding rules are things that are going through our machine, but we're not actually, using them, not actually, processing that traffic. Whereas input is stuff going into a process on our machine. So we would use forwarding rules if we're acting as a firewall or a router. We would use input rules to control traffic coming into processes within a server, right? So if it's operating as like a web server or a DICOM server, right? And for anything that a process is generating that's leaving our machine would be our output rules. So that's where we define all these different rules. So again, I talked about the forward rules, input rules, and output rules. Those are going to be our IP tables, right? The chain they're going to apply to one of those three. And if you were on a Linux machine and you run sudo iptables-l, uppercase L, it'll output for you what your IP tables rules look like. Most people don't really edit these rules. They use another utility like Firewall CMD or something like that on a Red Hat system, or Debian has its own utilities. And there's all these little utilities you can install, but really all of those utilities, all they do is edit IP tables, right? They're really just going at the lower level into IP tables to make these changes. So let's start to talk a little bit about DICOM, right? Why am I talking about firewalls with DICOM? Well, let's say you've got a modality, you've got a server, maybe it's a DICOM router of some sort, and then you've got a DICOM PAX somewhere. A lot of times we want to isolate our modalities from the rest of our hospital network, right? So our modality generates an image, and it's going to send that image to a device on port 1112 through a firewall, and then that device is then going to route that data. Oh, by the way, even though there's a firewall in the middle, all of that return traffic still flows back to the other machine because we allow established connections to flow back through that firewall, right? And then and because we allow, we have those established connections going back to that firewall, this is kind of a very secure way to configure this, where now that image can get routed from that DICOM node in the middle, can route it to maybe our PAX or a workstation or whoever is going to be using that data on the wider hospital network. And again, the return traffic works because it's an established connection. One of the things that makes this a very secure architecture is that in order for traffic to traverse from our protected hospital network to the, to get to a modality which is, isolated, as close to air-gapped as we can get, that can't happen, right? That traffic would have to go through that firewall to our DICOM router and then get from there to the other network, right? So this is a good mechanism. This is a good way to set up a DICOM network. You don't always have to actually have a firewall in both positions here. That DICOM software in the middle could have two different NIC cards and could act as a router. And you can use the route command in Windows, for example, or Linux. It has the route command as well to lock in different IP addresses to different networks so that the data can come in from the modality on one NIC and go out another NIC, get processed by the DICOM router and go out the other NIC to our wider trusted hospital network. And then we don't have to be so concerned about the software that's on our modalities, whether it has vulnerabilities and things like that. So now that we have a good understanding of TCP and routing and firewalls and so forth, the next thing I'll talk about is DICOM Communications. Right, the whole point of this video. We're 44 minutes in, and I'm just starting to talk about DICOM. But I'm going to try to put this in context for you in a little bit. But first of all, in DICOM, your client, service class user is DICOM's fancy word for a client, right? And likewise, an SCP is a service class provider. That's our server that's going to receive information, right? It's going to receive traffic. Generally, if you're curious as to whether something is an SCU or an SCP, if it's a client, if it's requesting some service, then it is an SCU, and if it's a server, it's going to be an SCP, right? Not all devices have both roles. Some devices are only one role. For example, modalities are typically an SCU, but not typically an SCP. Could they be an SCP? Sure, they could be, but it's not typical, right? So our first step in a DICOM communication is we have to establish a DICOM association. This all happens, right? So this first step I'm showing you, the DICOM association, is happening after TCP establishes our connection, right? So TCP is going to establish a connection first with that three-way handshake I showed you. Then once the three-way handshake establishes the TCP connection, now DICOM takes over and it does its own handshake. So it has its own three-way handshake. The SCU is going to send an association request message. Now, before I go further here, I want to break down what that association request looks like in DICOM. I want to deconstruct that a little bit. So if we deconstruct that, again, I'm just going to look a little bit like TCP standard, right? But this is an application layer message. First, you have the PDU type, the PDU length, the protocol version. You have your calling and called AE titles, right? Those are going to be in our association request. Then there's in that variable section, right? So they're all defined lengths, but then you have this variable section. And by the way, that's why we have the PDU length. It defines the length of the entire, so we know what these demarcations are. But then we have our variable section, which defines exactly what we're trying to do, right, with this association. So we'll have the application context name, and then we have we have another section where we provide multiple sections where we're going to have our abstract syntax and our transfer syntax. And you've probably heard these terms before, right? So the abstract syntax UIDs, that's going to be our what are we trying to send, right? Is it a CT, an MR, a presentation state, right? What kind of DICOM object are we trying to send? And then the how is what transfer syntax, right? So do we want ILE, ELE, JPEG, so forth and so on. So we're going to define that. Now, just a quick note on the transfer syntax. ILE, ELE, what is all this? LE is little endian, BE is big endian. They're basically just uncompressed TIFF formats, right? So they're very basic, but they're huge files. But you can also use compressed formats, which are much smaller files like JPEG or JPEG 2000 or RLE or something like that. But every DICOM SC and SCP is supposed to support ILE, meaning that in your DICOM association request, right? So this is a request message. And in the request, we tell, we're going to say who we are, who we're trying to call, right? That's our calling and called AE title at the top. Our application context name, and then we're going to list we're going to provide an abstract syntax UID that we want to send, and then we're going to list the various transfer syntaxes that we want to use. So in the request, we list an abstract syntax, and then we can list all the transfer syntaxes that we support for that abstract, not just one, right? We can list a whole bunch of transfer syntaxes. They can repeat. And again, those are going to be the SOP UIDs. We don't say JPEG, right? We put that long dotted decimal number, which is the SOP UID, which comes from the DICOM standard. There's also this section at the bottom I'm not going to talk too much about, the user info section. We'll skip that for now. But this is basically what that association request looks like. This is the type of information provided by that DICOM association request. One thing I want to talk about real quick is that the PDU in DICOM, the standard says the PDU has to be under 16,384, right? That's the maximum length of the PDU in bytes. So that's important. You can't, if you have an image, for example, that's larger than that, it's going to break it up into smaller pieces. And you'll see that here in just a few minutes when we talk about a C-Store. So we start with our association request, right? Again, this is all happening inside our established TCP connection. Then our SCP is going to send back an A association accept. If you want to see what that message looks like, you can go look in the DICOM standard. It'll, just like I did with association request message, it'll show you what the accept message looks like. Then our P datas go back and forth. The P data is basically our DICOM commands and DICOM data, which I'll talk about next. When we're done with our connection, we send a release request. A release response is sent by the SCP, and our association is closed. You can also, before the connection is even established, the SCP could send an association rejection. So when we get that association request, if there's something in there that we don't like, right? Maybe it's the calling A title, maybe it's the called A title, or it could be the transfer syntax that we don't, maybe we don't support any of the transfer syntaxes they gave us. Maybe we don't support the abstract syntax, right? Maybe we don't know how to deal with CT images, so we can reject that association. So that's one thing that could happen. Then we'll never get to that P data phase, right? We don't get that far because we reject it. And even while that P data phase is happening, we can send an A abort. So at any time, the SCP can send an A abort message, and at any time, our SCU can also send an A abort message. If we have an A abort, right, so if the SCP sends an A abort to an SCU and it's not done with communication, it'll generally accept that abort. So the next message it sends back will indicate, if it's P data, if it's in the P data phase, the next message that comes back will indicate that it's the last message, and then the connection closes. And there's no formal release, right? There's no A release response. It's just an A abort. And there should also be information in that abort as to why you're aborting it, and I'll talk about some of those statuses that we have in DICOM that do that. But either way, so this is the association. You can think of it like our TCP handshake. It's setting up and breaking down the connection. And really, the actual DICOM communication is happening within that P data phase in the middle, right? So we can break that down, right? So on this next slide, let's talk about what's actually happening in there. As an example, a C-Store, which is when we're sending data from an SCU to an SCP, right? Let's see what that looks like. So after our connection's been established, because we got our association request, we then send a C-Store request, right? So a C-Store request message goes out. I don't want to break down this as much as I did the association request, but the important point is you've got two flags in our P data. The 8th bit is whether you indicate whether it's a command or data. So it's a 0 or a 1. I have a typo here. That should be 0 or 1. So a command is 1, data is 0, not 2. I don't know why I put 2 there. It's a 1-bit field, right? So a 0 is data. And then the 7th bit is 1 if it's the last message, and 0 if there's more messages for this request, right? So in my C-Store request, the first C-Store request message is going to have a 0 and a 1, meaning that it's not the last message, and it's the command. It's basically saying, I want to store a message, right? I want to store some DICOM data with you. And it's going to provide information about what we want to store, right? It's going to establish some identity for this communication so we can reference the different parts of this data that we're going to get in here in a few seconds. There's other information like this. It'll tell you what the SOP instance UID is for what you're trying to store. It tells you what the class UID is, right? So, is it a CT, an MR, so forth. The command is obviously going to be C-Store, right? So you would reference this as a C-Store. So with this message, I'm basically saying I want to store an image. Here's what the image is. This is the type of image. This is who requested that I store it with you. That's the move originator AE. And the move originator message ID, right? So if we want to keep it in context with a CMove, which I don't really talk about in this presentation, but in any event, once this C-Store request comes in, then the next packet is going to be, I'm going to take that image, right? So let's say it's a CT image, right? Maybe it's too big to fit in a single PDU, so we're going to break it up maybe into 4 parts. So each one of those parts is going to have our message data set. Now notice that my flag now, that eighth bit is set to a 0, meaning that now I'm sending you data, right? And somewhere in that, I'm not decomposing this anymore, but it would reference the original C-Store request, right? All these different parts. So I'm gonna keep sending these different parts. Eventually, I'm gonna be done, and and how do I know I'm done? Notice that the flag is set, right? So last message flag is set to a 1. Now my SCP is going to take all this information it got. It got the C-Store request. It got a whole bunch of data. It's going to put it all back together again, and then it's going to say, okay, this is successful. I have all this data. It makes sense. It passes whatever basic checks it might have, and it's going to send a C-Store response. That C-Store response, again, it's going to be a command, so we set that to a 1, and it's going to be the last message, right? Because it doesn't have anything else left to say. And either at this point, the SCU is going to begin the process of releasing the association, or it'll abort the association if it doesn't like the C-Store response. That C-Store response could also indicate some failure, right? So it'll have a status. the status could be success, warning, failure, cancel, pending. If it's a warning or a failure, there's codes in DICOM and the DICOM standard that can reference exactly what that failure is. So it can tell you why it failed, right? So that's going to be your error message in DICOM. The SCP is going to say, look, I can't take this, I got all this stuff, but I can't process it for this reason, or I didn't get all this stuff. Something looks like it's wrong. Maybe the checksum doesn't match or something like that. So that's going to be our status message. All right, so now that we understand all that, let me try to put this back in context for you. So I talked about the data link layer, which is a frame. Then I talked about the network layer, which is our packet. Then I talked about transport, and in the transport layer, our segment establishes the connection. And then once we had that established connection, we talked about how DICOM creates a connection, right? So at the application layer, we create this DICOM connection with the association. And then and then I even broke that down, right? I took the association request and I showed you what that association request looks like. And then I took the actual data, right? I showed you what it looks like to do something like a C-Store, which happens inside the association. So there's a lot of layers here, right? And when you look at this, I talked about a lot of stuff at all these different layers. You can see how, DICOM relies upon a lot of skill sets, right? We have a skill set at the data link layer, the network layer. So you have to know networking. We have to know that transport layer with TCP. And then we have to know all the DICOM level communication stuff that I talked about. And everything is encapsulated, right? So, at the application layer, we have our DICOM image, which gets encapsulated in that C-Store request, which is encapsulated in the association request, which is encapsulated in a transport layer, three-way handshake, right, in our segment. And then that gets encapsulated at the network layer. And then that's all encapsulated at the data link layer. And eventually it's all just ones and zeros on the network, right, at the physical layer. So I just wanted to kind of give you an idea of how all this ties back together, right? And there's a lot more depth that you could get into with DICOM, but this is just the high-level overview. So there are some other DIMSE-C commands. I'm not going to talk about the N commands in this presentation. I can do that in another presentation, but some of the other I talked about a C-Store. You have C-Find, which is how we find information on a DICOM SCP. So it allows us to interrogate and query DICOM devices and see what it has. We can tell a DICOM device to move a study or move DICOM information. We can say, I know you have this information. I want you to send it to someone else, right? That's going to be a C move. There's also C get and C echo. C get is where, it's sort of like a C move, but I can go out and say I want to get some information from you, but it's only one specific instance, one specific SOP instance UID. And that's probably one of the only times that as an SCU, the data is going to flow from the SCP to the SCU, would be a C get. And it's not that common. I don't really see that very much in DICOM networks. Most people are using a C-Store, a C-Find, and a C-Move. And then a C-Echo lets you validate DICOM nodes on the network. Again, you can learn a lot more about those in the DICOM standard, or I can do another video that discusses those. But that said, since we're talking about DICOM communications, what we're talking about here is DICOM communications using TCP at a very low level. But DICOM also supports, also in part 18, it talks about DICOMWeb, right? Which is WADO, Keto, STO. This allows us to leverage web services. So it's a much more modern approach to DICOM communications. Modern if you consider 1997 to be modern, because that's when all these standards for web services really started popping up, right? XML, SOAP and things like that, and REST. They all start to kind of crop up starting in 97 and going forward to today. So, this stuff's been around for 20 years, but we're still kind of struggling to adopt DICOMWeb. I think you'll find that by and large, as I'm recording this video, probably 90% of DICOM communication, maybe even more than 90%, is still everything I've talked about before. It's not really using DICOMWeb yet. But the hope is that in the future, we're going to be using these RESTful web services to interact with DICOM services, as opposed to using this older approach with TCP with these low-level communications. And why is that a good thing? It's going to be better aligned with things like HL7, because HL7v3 is web services, Fire is web services, XDS, which uses EBXML, which is an OASIS standard, that's also web services. So you kind of get this sense here that if DICOMWeb is a RESTful web service, and so are all these other standards that we work with, you could start to use things like XSLT to bridge the gap between these different services or these different standards, and it could make some interesting workflows in the future where maybe this stuff will be a lot more interoperable in the future. HL7 and Fire and XDS and DICOM can all kind of live in harmony together, right? That's the dream. One thing I just wanted to talk really quickly about is, now that you have this sort of understanding of TCP, and I talk about DICOM, some advanced TCP tuning that might be have an effect on DICOM. There's lots of different things in TCP. I kind of just scratched the surface here. There's a lot of things in TCP that you can tune that can help with performance with DICOM, because DICOM is, we have a lot of very large data sets with DICOM, right? We have these huge data sets, and it's a little different than a lot of other TCP traffic. So what I like to do is just talk about, I talk about TCP and DICOM, is that there are special things that we have to worry about. One of those is the Nagle algorithm. So John Nagle was a guy that came up with this buffering algorithm to make TCP more efficient. And I'll explain why they did this, right? So let's say you're a ferry boat captain, right? I got a river on my screen here, and my ferry boat's on pardon the crude drawing here. The box is supposed to be a ferry boat. But let's say I've got 6 cars ready to go on the ferry, right? So I load these 6 cars in the ferry boat, and I'm the captain of the ferry boat, and I say, okay, I've got 6 cars, I'm ready to go, because I'm completely full, right? I can't fit any more cars, so it's time to go. Easy decision. So I cross the river, unload those cars, and while I'm across the river, 2 more cars show up, right? And I'm across the river. So I go back, I load the next 2 cars. But now, as the ferry boat captain, I have to decide, do I wait for more cars to show up, or do I just cross with the 2 cars that I have and then come back, right? And if somebody shows up while I'm gone, tough break, right? So my ferry boat captain waits, and luckily he waits because somebody else shows up, so now I can get some more cars on the boat, and then I cross the river, right? Then I come back, another 2 cars come across, and now as the ferry boat captain, I say, well, last time I had just 2 cars. I waited for a while and somebody showed up, so I'm going to wait, right? Now the ferry boat has to make the decision, the captain. He has to think, how long am I going to wait for more cars? Because now I'm wasting time for the people that are on my ferry boat, and it's going to reduce the efficiency, right? So he might just shove off with those 2 cars. Luckily, no one else shows up. But the important thing here, what I'm trying to convey, is that the Nagle algorithm is like that ferry boat captain, where you're trying to figure out what's the amount of time that I should wait for more cars before I shove off. Now, let me explain why this is important for DICOM. Think back to the DICOM Association for a C-Store, right? With a C-Store, we have the bulk of our data is moving in one direction, right? We have very small messages to establish our association. We have a small command message to establish the fact we want to store an image. We've got some control messages coming back the other direction in DICOM. And then we've got our 16384, PDUs that have our actual data that are being sent across in those P data messages. And then eventually we shut down, we tear down that association. But if you think about it, there's lots of different sites that, some messages are really small and some of those messages are really big. There's no in between, right? So if you have a computer that's implemented the Nagle algorithm, which almost all network systems do, it's going to analyze this traffic and try to decide, it's going to try to figure out, okay, well, before I had a really small packet, and but later a bigger packet came in, so waiting would have made sense. And sometimes it doesn't make sense to wait, right? But the thing is with DICOM is DICOM already has this sequence of events that have to happen. And we don't really care about buffering in the sense that we don't need the operating system or the sockets libraries in Windows or Unix or what have you. We don't need that to figure out how to optimize the buffering. We already know how to do that in DICOM. We already know when those packets have to move across the network, right? We already know when those segments have to fly across the network. So in many cases, we can get a lot of performance just by shutting off that buffering mechanism. Either we can shut off the buffering mechanism, or we can tweak the settings in the buffering mechanism to make sure that it's going to be amenable to how DICOM communicates. So there's all these little settings. So, and if you're wondering, in Windows, you can go in the registry and you can adjust how it handles Nagle. When you write a DICOM application, you can, when you bind to the sockets library, you can tell it how to handle buffering. In Linux, you can do the same thing. In Unix, you can go in and you can adjust how this works, and you can really tune to get much faster speeds. So sometimes if you're wondering why you've got two DICOM systems that are in similar environments, and one's really fast and the other one's not quite so fast, and everything else is equal, this is one of those little things that you might have to look at. There are other things in TCP. I would encourage you to learn more about TCP and how it works, because there's lots of other little settings that we can look at in TCP that would affect performance on a network. All right, that's it. Thank you for watching.